Hello everyone, I'm excited to present our project on AI cough detection using neural networks. I am Divya and my teammates are Priya Krishnamurthy and Mohammad Faizan. And we have developed a system that leverages advanced neural networks to distinguish cough sounds from non-cough sounds within audio files. The primary purpose of our project is to effectively identify cough from a blend of audio sources. Our first outcome was to achieve superior accuracy in classifying cough versus non cough sounds. Secondly, we wanted to advance applications in health monitoring systems where accurate detection of cough is essential. Lastly, we wanted to demonstrate the robustness of convolutional neural networks in processing and classifying complex audio data. We have attached the dataset link in our slides. To give you an overview of our data set, it consists of it is a semi-labeled collection of audio samples, which included over 1,000 samples. The pre-processing methodology we used was to systematically classify and segregate audio files into cough and non-cough categories. Coming to the format of the data we used, the data set composed of audio recordings which captured a wide range of sounds, including coughs, ambient noises, and human non-cough vocalizations. Each session is encapsulated in a distinct file which contains synchronized acoustic streams which were taken from a body-facing mic. For the data encoding, it was stored in high-quality audio formats like WAV, ensuring minimal loss of information. Also, we have converted the semi-supervised dataset into a supervised dataset by running the script and classifying the three non-cough sounds into one category. The baseline model we selected was a CNN model. The reason we picked a CNN over an RNN is that the CNNs are optimized for spectrogram analysis. Additionally, they also possess computational advantages. Coming to the implementation details, for the data preprocessing, we transformed raw audio into spectrograms before feeding the data to the model. Also, we implemented convolutional layers and max pooling layers to extract important features from spectrograms of audio data. Lastly, we incorporated dropout layers to prevent overfitting. Some of the software and libraries we used were TensorFlow, Keras, and Librosa for audio manipulation and processing. For the feature extraction methodology, we first converted the audio signals into Mel frequency cepstral coefficients or MFCCs that capture the pitch and texture of sounds. Next, we normalized and padded the MFCC data to ensure that the input size was consistent to feed into the CNN model. Uh, Coming to the model learning performance and progression, we initially noticed an accuracy of 59.76%, which finally was converted to 90.75%. Additionally, we noticed a loss reduction over epochs, and as compared to random classification, our model was far more superior and was far more superior. The objective of the loss function is to measure the discrepancy between predicted probabilities and the actual class labels. And minimizing the loss function ensures that we have optimal performance. One observation that we had from the graph attached was that the validation loss was much lesser than the training loss. Coming to the accuracy graph, we observed that the accuracy increases and the loss decreases over epochs. Lastly, in order to observe the baseline results, um, we finally the model predicted the labels as 1 for cough and 0 for non-cough audio samples.
So the data flow diagram that we used throughout the model was that first we took the audio signal in WAV files, then classified it into non-cough and cough. That is, we labeled the data. This was then converted to MFCCs, and then these MFCCs were fed into the artificial neural network and the CNNs. The first improvised model we provided is an improvised version of the first baseline CNN model. But before we did this, we improved our data by adjusting the FFT parameters, and also we padded the MFCCs so that they have uniformity across all the inputs. The revised CNN model had adjusted padding and also pooling layers, adjusted pooling layers. We chose categorical cross entropy as the loss function and used Adam optimizer for efficient training. Finally, we had a classification of cough and non-cough audio clip on this model as well. This graph represents the accuracy graph, and we can see a higher training accuracy of almost 99% and a very robust test accuracy of 98.93%, which shows that the model performed really well on the testing data. This graph represents the loss function, and we can see that we are able to minimize the error over the various epochs. In our histogram, we are trying to show that there is a very small gap between the predicted data that is predicted data and the true data, and only few samples are predicted incorrectly. This highlights minor discrepancies. The second model we are providing here is LSTM. The reason we decided to do this was to test how our data performs on an RNN, and we decided to use bidirectional LSTM so that we have the context of both the past and the future. Additionally, for this model, we also added model checkpointing and early stopping so that whenever the training plateaus over a particular accuracy level, we can stop and later on take instead of wasting more epochs. We also implemented L2 regularization, and we had increased dropout rates so that there is no overfitting. In this model as well, we use the same data pre-processing, that is higher padding for MFCCs and better FFTs for efficient uh, uniformity across all the inputs. And we used Adam optimizer and categorical cross entropy here as well. And again, a model classified into cough and non-cough sounds. This is our training accuracy. The training accuracy was pretty high for our LSTM model at 99%. However, it did not perform so well on the test and validation data, and the accuracy was capped at 93.11%. Again, our model shows that the loss reduced over the various epochs, but there is a scope of improvement when it comes to model robustness. Our histogram shows that again there's a tiny gap between the predicted values and the true values. There's only few values that are predicted incorrectly. Let us compare the result of all the three models. You can see that the improvised CNN model performs the best. The major reason for this is all the hyperparameters were tuned perfectly in order to achieve both a high training accuracy and as well as a test accuracy. And you can also see that it performs really well when it comes to the F1 score and precision. So our baseline model initially achieved an 86.31% test accuracy, while both our improvised models achieved a higher accuracy at 98.3 for CNN and 93.11 for LSTM. What are our key takeaways and learning from this particular project? We realized that using bidirectional LSTM, CNN, and other hyperparameter tuning like batch normalization and changing the learning rate of the optimizer can really help us improve the performance. And detailed pre-processing is truly needed in order to achieve a higher accuracy in audio classification. The future implications for this project is that it can be used in health monitoring and medical diagnostics applications. And this also encourages ongoing advancement in audio signals and processing techniques. Thank you so much for listening to our presentation today.